All right, welcome back. I'm going to talk you now through question 3 to this homework task. So as we can see, we have to determine the minimum distance of the graph of each of these two parabolas that we found in part 1. And we have to find the minimum distance of these two parabolas from the point 0, 0. So we need to use this distance formula that's being given to you here. So I thought I might show you a visual of what we're trying to find here. So we have here, this is the first parabola that we found in part 1. So I've labeled it here in red. And you can see that the black line there is the distance, or the line segment that connects the coordinate 0, 0 to that parabola. And as we can see, if we change the value of x, we can see that's the line segment between 0, 0 and the parabola. And the question is asking us, where is this line segment at a minimum? So where is the minimum distance between these 2 points? So all I've done here is I've just plugged in the equation f of x, and I've also then found the equation of the segment that connects the point 0, 0 and this point. So as you know, if we're trying to find the distance between 2 points, we can just use our formula for a linear equation, which would be if we have the points x1, y1, and x2, y2, we would have that y minus y1 is equal to y2 minus y1 over x2 minus x1 times x minus x1. So that's just the same as the point gradient form of the linear equation, where this part here is just the gradient. That's how I constructed that equation there. Now I've also plugged into Desmos this distance equation, so the distance between 2 points. So you can see I'm going to bring that up now in blue. So you can see here what I've used is the basically some arbitrary point that lies on that parabola, the distance between that and the point 0, 0. So let me show you how I did that. So what we're basically going to do is we're going to use this equation here. We want to find the distance between these 2 points. So let's let our x1, y1 be the first point. So that's the point 0, 0. And we're also going to let x2, y2 be any points on this first equation. So any point on that equation 1, well, it's going to have an x value of whatever x is equal to at that point, and it's going to have a y value of this equation. So the y value will be defined by this equation right here. So y2 will be 11 over 3 x cubed plus a half x minus 7 over 6, so the equation that we found in the first question. And you can see that if we plot this on a graph, the question is really asking us when is this distance at a minimum? And as we can see, if that's in blue, if that's the equation of that distance between those 2 points, we can quite clearly see that the absolute minimum occurs right here. There's also another local minimum over here, but if we compare those 2 points, we can clearly see that 0.47 is less than 0.62, so clearly this must be our absolute minimum. We can also do this on the CAS calculator. So if we bring that up, how you might do this is we would first define our 2 equations. So if you remember from part 1, the way we can do this is we can go action, command, define, and I'm going to define the equation f of x is equal to, and I'll just type in what we found last time. So we have 11 over 3 x squared plus 1/2 x minus 7 over 6 defined like that. We also need to define our distance formula. So we'll go action, define, and like I did over here, when I plug these things into the equation that we have here, we can see that d is going to be equal to the square root of the difference between the x values. So if x2 is x and x1 is 0, it's just going to be x minus 0, which is just x. So that's x squared, plus the difference between the y values, which is this y value. So that's the equation f of x. That's how I defined it on the CAS. So the equation f of x, y2 minus y1, so it's that minus 0, so it's just f of x. So this is the equation for the distance between those 2 points. The square root of x squared plus f of x squared, where f of x is the equation of that first parabola. So let's just go ahead and define that. When you're defining functions on CAS calculator, you can just use a function that you've predefined in your definition. It carries down. So if we go ahead and do that, we can have the square root of x squared, and I can just type plus fx squared. And yeah, the CAS will just insert that function that I've defined above into that. So if I go ahead and graph these two things, if I go over to the graphing screen, the CAS will remember what I've defined as f of x. So this needs to be set to equals, we type in f of x, there you go, there's the parabola that we defined on the other screen. And if I type here d of x, there is, I don't know what happened there. So we'll just go back to the main screen to define this. X squared plus f of x squared. That's correct. Let's try again. So we'll go zoom out, fully graph these two things. Doesn't seem to work on the CAS. I guess let's type it out in full. So we've got the square root of x squared plus f of x squared. Hopefully that works this time. Oh, interesting. Well, I guess it worked for us on Desmos, so we can clearly see that the absolute minimum is going to occur right here. And I guess if we want to verify that, if I set A here, which is the what we're defining the line segment, if I change that value of A, we can see that it does appear to be that that line segment has a minimum length somewhere around here. And according to this absolute minimum, it appears to be 0.47. So if I change this to 0.47, that does look like a pretty short length. And apparently the length at that point is 0.485. So a follow-up question might be, what is the minimum length? So it's 0.485. So that would be the answer to this question. For equation 1, the min length occurs at approximately, well, at x is approximately equal to 0.47. And at this point, the distance between these 2 points is equal to the y value here, which is 0.485. So where d is approximately equal to 0.485. Okay, so that's the first one, and I'll just repeat this again for the second equation just so you can kind of make sense of it. So if I switch off these first couple of graphs, let's look at the other parabola that we found. So this is the other parabola. What we're trying to find is the point where this line segment, the distance from 0, 0 to that parabola is at a minimum. So if I go ahead and vary the value of A, you can see that's the line segment. So the distance from the origin to the parabola, where is that distance at a minimum? So again, we can just use this definition. So we've predefined g of x. We have the square root of g of x squared plus g of x. We can see that's the graph of the distance equation, and quite clearly we can see that that equation has a minimum right here. So if we just change the value of a to make it line up with that, that's 0.46. So 0.46. We can see that line segment there, that does look like the minimum length between the origin and the graph, so our answer makes sense. And apparently the length there is going to be about 0.51, so we can type this in as our answer. So for equation 2, min length occurs at x is approximately equal to 0.46. And at this point, the distance from the origin to the parabola is approximately equal to 0.51. And if you had to do this in a SAC, maybe you might get given units of some description, so just make sure you give your distance in the appropriate units. But that is how you might solve this sort of problem if you're required to find the minimum distance between a particular point and a parabola. And notice that this might not necessarily be the origin. So have a think about how could you solve how could you find the minimum distance between a given function and some arbitrary point? So maybe you can repeat this for yourself as an exercise. What is the minimum distance between these two parabolas and some other point? So let's say the point 0, let's say 2, 3. I don't think that appears on either of the graphs. Otherwise, it would be that one does. So, yeah, that should be fine. I don't know, let's choose a more arbitrary point. Let's say the point 4, 5. So this is an exercise for you. What is the minimum distance between each of these two parabolas that we found in part 1 and the point 4, 5? So give it a shot for yourself. Maybe you can use Desmos in your answer and see how you go. And feel free to tell me what you get. All right, thanks for watching, and I'll see you guys next time.